Today, lesson 36b, an application of the Pythagorean Theorem, which we talked about yesterday. And before we actually get into the distance formula, we're going to talk about two different proofs of how the Pythagorean Theorem works. And so that will be our focus for today. All right, so let's get started. Yesterday we talked about the Pythagorean Theorem. There are many proofs of the Pythagorean Theorem, and if you were to Google it, you would see all of the different ones. Some are more difficult to understand than others. I've tried to pick a couple that were fairly easy to understand, and really all they involve is your understanding of area in geometry and doing a little bit of algebra. Okay? So here's our first proof, the one that's in your notes to the left. So I start with a square, and with that square, I'm going to, obviously all squares have four right angles in the corners. I'm going to divide each side into a section of A and a section of B. So what I mean by that is that this side right here has a length of A plus B. And we have that flickering issue again, and I'm not quite sure why. So this square is A plus B by A plus B. Okay? And so, to find the area of that, I'm going to compare two different things. I'm going to compare the area of the outer square, which this is the outer square, so that's A plus B times A plus B, base times height, or side by side, or however it is that you want to think about that. And inside of that, I'm going to put a blue square that is C by C. And if you look at your picture, this is now what your picture looks like. So another way of looking at this would be this square is 4 right triangles and 1 blue square. So if I could prove that the outer square area was equal to the area of all the pieces that make it up, and I think you can clearly see there are 4 right triangles there and 1 blue square on the inside. And so that would be 4 of the triangles, and to find the area of a triangle, it's 1/2 the base times the height. And all I'm doing here is I'm 4 of these right here. Or maybe it's better to look at this one right here. To find the area of any triangle, it's 1/2 the base times the height, plus the area of the square. So here, these are the 4 right triangles. There is the area of the square. So if I could prove that these two sides are equal to each other, or equivalent, I could prove that the Pythagorean theorem has to work. All right, so if I use the double distributive property on the left-hand side, I would end up with a squared plus 2ab plus b squared. If you did the double distributive property, that's what you would end up with. And then on the right-hand side, if I multiplied the 4 times the 1/2 ab, that ends up becoming 2ab. All I'm doing here is I'm doing some simplifying. Now remember, what I'm trying to make this look like is I'm trying to make this look like a squared plus b squared equals c squared. So in order to make it look like that, if I subtract 2ab from both sides, I have a squared plus b squared equals c squared. So this is one very popular proof of the Pythagorean theorem. Now remember, how I got to here from this step right here is I subtracted 2ab from both sides, which left me with a squared plus b squared equals c squared. All right, so that's one proof of the Pythagorean theorem. Another very popular one was actually an original proof by a former president, James A. Garfield, and I'll read what it says up here. The Pythagorean theorem has been proven many times, as I said a few minutes ago, and probably will be proven many more times. But only one proof was made by a United States president. 5 years before James Garfield was elected president, he came up with a proof that involved a simple sheet of paper and some scissors. Before President Garfield went into politics, he wanted to become a mathematics professor. He had a lively interest in math and studied even after he decided to run for Congress. One day he came up with a simple proof of the Pythagorean theorem, and that's what our next one is based on. So here's what we do. We start with two congruent right triangles joined together such that the long leg of one forms a segment of the shorter leg of the other. So it looks like this. And you have that already in your notes. Okay? Now, and this is where you're going to need to start writing, if we connect them, what shape have we formed? So you can see that I connected them together with that line segment. Anybody know what the name of that shape is? I'm talking about the entire outer shape. So let me kind of highlight that. I'm talking about this shape. Right, it's a trapezoid, exactly. And we all should know how to find the area of a trapezoid. So we've connected them, and we now have a trapezoid. So from here, I'm going to take really a similar approach that I took with the other one. I'm going to compare the outer trapezoid area and compare it with all the pieces that make it up. But before I can do that, I have that white triangle right there, and that was basically part of the point of today's warm-up. If before you can claim that that is a right triangle, you have to prove it and not assume it. And we will come back another day and I will prove to you that that really is a right angle there. So if I claim that that's a right angle, then now it's very easy to deal with. So I have the area of the outer trapezoid. And to find the area of a trapezoid, you have to remember that it is 1/2 the sum of the bases times the height. And so basically, the sum of that base and that base is where this a plus b comes from. And the height is right there. That's where we get the other a plus b. It's 1/2 the sum of the bases times the height. Now, like the other problem, I'm going to say that that has to be equal to the sum of the areas of all the pieces that make up the shape. Well, we have two yellow right triangles and then a kind of a tannish right triangle there. The yellow ones are all 1/2 times a times b, and the tan one is 1/2 c squared. And so that's where I get this part right here. And I'm going to stop for just a second to let everybody get caught up. All right, much like the last one, I'm going to do some simplifying on the left-hand side by using the double distributive property to multiply out a plus b times a plus b. And then I'll do some simplifying on the right-hand side also. So that's what I've done so far. A plus b times a plus b, like in the last problem, is a squared plus 2ab plus b squared. And then on the right-hand side, 2 times 1/2 ab is ab. So I've done a little bit of simplifying. Now, I'm going to multiply both sides by 2. We've done that kind of thing many, many times. I do that to clear out the fractions. And so when I do that, I now have this. And I've explained that idea of multiplying everything by the common denominator before, so that should be fairly clear. And then now, like in the last problem, I'm going to subtract 2ab from both sides, because at this point we're exactly at the same point we were in the last one, and I've proven that a squared plus b squared equals c squared. So I'll stop for a few seconds. That's a couple of proofs of the Pythagorean theorem. There are many more, but these are two of the easier ones. So let's get into our main topic for today, which is distance formula. So here's a problem. Rollin went on a hike to visit a cave in the mountains. To begin his hike, he faced west and hiked for 3 miles, then turned to the south and traveled for 2 miles. After a water break, Rollin again continued west for 4 miles, and really this is just an extension on a problem we took a look at yesterday. Turning north, he continued for 3 miles. Next, Rollin turned left for 2 miles. Then he took a right and continued on his hike for a final 6 miles until he discovered the location of the cave. How far is the cave from where Rollin started his hike? Well, if I map it all out, and you do have this grid, this coordinate plane in your notes, it would go something like this. He went west 3 miles, then he went south 2 miles, and I know that first blue line is kind of hard to see. Then he went west 4 miles, Then he went north 3 miles. Then he went left 2 miles. Then he went right 6 miles. And I think that last one should say not right. This should actually say up or north. Now the question is, this is where he just ended. How far is it from where he ended to where he started? Well, one thing that we could do is we could do this. We could connect those two and then make a right triangle out of that and use the Pythagorean Theorem. So the vertical distance is one thing, the horizontal distance is another. So it's 9 miles of horizontal distance and 7 miles of vertical distance. So from there, we could use the Pythagorean Theorem. And so I'll do all that work for you. It ends up being the square root of 130, but since this is more of a real-world problem, we need to convert it to the tens place. So that would be 11.4 miles. But the idea today is, what if you don't want to map all of those kinds of things out like that? How could you figure out the distance without making the drawing every single time? Well, that's where the idea behind the distance formula comes. So let's go to the back side of your notes. All right. What if, as it says in the blue rectangle there, what if we don't want to plot the ordered pairs and draw a right triangle and then use the Pythagorean Theorem? Well, there's a formula called the distance formula, and it is based on the Pythagorean Theorem. So if we wanted to find the distance between those 2 points right there, we would need to create a right triangle and find the y distance and find the x distance. And if we put that together with the idea of the Pythagorean Theorem, we end up with d squared. D represents distance. The a, I'm going to use the x, the difference of the x's squared. And all I'm doing right now is I'm showing you how the distance formula is derived. And then if we take the square root of both sides, we have the distance formula. So I'm going to stop for a second to let you get caught up. And while you're copying that down, much like the slope, x sub 2 represents the second x in our ordered pairs. The x sub 1 represents the first x in our ordered pairs. The y sub 2 represents the second y of our ordered pairs, or the y in the second ordered pair, and y sub 1 is the first y, or the y in the first ordered pair. So distance formula, once again, is the square root of the difference of the x's squared. And when we're using the Pythagorean Theorem, that's how we find this length, the difference from one end to another, plus the difference of the y's squared. And when we're using Pythagorean Theorem, that's what we do to find the length of that side, one point from another. So, number 2, find the distance between 4, -7, negative, negative 12. The long way would be to take and plot those on a coordinate plane, make a right triangle, and use the Pythagorean Theorem. Or we could use the distance formula. We need to make sure we pay attention to our signs here. Second x is -8, first x is 4, second y is -12, first y is -7. So we end up with this. If you're going to make a mistake, it's going to be right here. Be careful with that. So we end up with -12 squared plus -5 squared, the square root of that. So that's the square root of 144 plus 25. That's the square root of 169, which is a perfect square. So the distance from 4, -7 to -8, -12 is 13. Everybody try number 3. Now the same rules apply if we end up with something that's not a perfect square, in other words, something that's irrational. We need to simplify the radical. All right, using the distance formula, substituting 8 for x2 and 12 for x1 and -2 for y2 and 1 for y1, we end up with this. Do a little bit of simplifying. Multiply out the perfect squares. We end up with a perfect square here, and so the distance is 5. All right. Now, everybody do number 4 and number 5. If we end up with an irrational square root, in other words, a square root that's not a perfect square, simplify the square root. And once again, do number 4 and number 5. Number 4, same idea. The only difference between 4 and 5 and 2 and 3 is that we end up with a square root that's not a perfect square. So in that case, we simplify the radical. So we plug in our x1, x2, y1, y2. We end up with 4 minus -2 squared, the square root of that whole thing, plus -1 minus 5 squared. So we end up with the square root of 6 squared plus -6 squared. And that would give me the square root of 72. And that's not the first time we've seen the square root of 72. That would be 6 square roots of 2. Number 5, same idea. Substitute our values in. Do a little bit of simplifying. And continue simplifying. We end up with the square root of 160. And I know that that can be simplified. That is 4 square roots of 10. Any questions about any of the problems in 2 through 5? All right, so an application of this. What if we had a triangle that looks like this, and you're asked to find the perimeter of that triangle? Think about how you would do that for a second. All right, have a quick discussion with your shoulder partner in full detail on what you would have to do to find the perimeter of that triangle. So we need to find the perimeter. To find the perimeter, we need to find the length of each side. So for side AB, use the distance formula with those two ordered pairs. So that side would be the square root of 50, but it makes more sense in this problem to, especially since it says to the nearest tenth, to figure out what that would be to the nearest tenth, and we all know how to do that. So side AB is 7.1 to the nearest tenth. Now I'll go with side BC. Use the distance formula on those two ordered pairs. That would be the square root of 37. And to the nearest tenth, that would be approximately 6.1. Now to fully find the perimeter, I need side AC. Use the distance formula again. That is the square root of 61. And to the nearest tenth, that is approximately 7.8. So now to the nearest tenth, I have the length of all three sides of the triangle. Find the sum of them, so that means the perimeter is approximately 21.0 units. Any questions? All right, we are finished for today.